Okay, so off we go. Here's where we were last time. We were talking about this new kind of an integral. It addresses this sort of weird situation where we have a domain that is what I like to call dimensionally awkward, right? So this is a domain that itself is one-dimensional, but it lives in a space that's two-dimensional, possibly three-dimensional, right? But certainly not the same as the dimension of the domain itself. So what we figured out as a way around this is to kind of rip off the big idea of how we did change of variables, which was another case of we have an undesirable domain that we don't like. And so the big idea is view it as being an image, right? In this case, a curve viewed as an image, well, that's parametrizing the curve. And then with that idea, you use the pullback stretching factor strategy to rewrite it as an integral on this new, nicer domain. In this case, what we might call dimensionally nicer. This is dimensionally at home. It's a one-dimensional interval that lives on the one-dimensional t-axis, and that's something we know how to do. Okay. So we did several examples last time. And now we're going to proceed along and try to continue with more examples. So this next one concerns work. And I'm sure you all recall early in this class, we sort of upgraded our formula for work, right? The old high school formula for work is just a scalar force times a scalar distance. And then with an asterisk where there's this long discussion about how, well, yeah, it needs to be in the same direction. And if they're not, then you've got to look at the component. And how do you compute components? Well, cosine, blah, 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 a bunch of stuff. Right? So it's kind of an awkward formula. We improved that significantly by realizing you can just rewrite it as a dot product. And a lot of that asterisk just disappears. That said, it does remain that when you're talking about work, using this formula, we are assuming the force is constant over the entire displacement. So there is that. And we are assuming that the displacement is in a straight path. So that's another little asterisk, I suppose, that remains. So what we want to do now is consider, what if I try to remove these asterisks as well? What if my force is not constant? As, for example, this vector field representing forces right here, conspicuously not constant. Right? So can't use that formula, so what do I do? And then analogously, what if your displacement is not over a straight line path? What if you are moving along a curved path? Again, like so. How are we going to deal with this? Okay, so the big picture, I'm going to skip over a critical detail just for a moment. The big picture is what we have right here. Chop it up into little pieces. That's kind of how we answer all accumulation arguments in this class. Chop it up, add it up. Right? We take our curve and chop it up into little pieces. And on each little piece, so for example, this little teeny tiny little bit of curve right there, well, that's approximately straight. Not exactly, but in the round off error, it's going to go away. And it's such a small, presumably, little piece of curve. Those points on this curve are not separated by very far, which means that the vector field doesn't have that much time to change, which means the vector field is approximately constant. So on the individual pieces, we really can use this old formula, just force dot displacement on each individual piece. And then you add up over the entire curve. And we're going to write all the details for that down on the next page. Before we do that, though, we need to recognize something fundamentally different about this question that does not apply to any of the other examples we've seen previously. And that is that when you follow this path, it really matters which direction you go if you're computing work. So imagine, for example, that the forces here represents the force of, walking uphill. And, different uphill is a different direction depending on where you are on the side of the mountain. Okay. If I'm walking as indicated here, if this is a lower altitude, and looks like that'd probably be a higher altitude, walking uphill is going to take more work than walking downhill, where I can just put on a pair of roller skates and let's go. How are we going to deal with that? We've never seen anything like this before. Let's look at the previous examples that we've seen. Painting the fence takes the exact same amount of paint whether you paint clockwise or counterclockwise. It's completely got nothing to do with direction, right? Likewise, looking back here at where we had this irregular wire, and for example, we were computing mass with a scalar line integral like so. The mass of a wire, there's no notion of direction. The mass is the mass, end of story, right? You can count the mass in whatever direction you like. It doesn't matter. So we have a really fundamentally different situation here. And we should not expect that the construction that we use to compute mass and area and stuff like that, we shouldn't expect that construction would work here. After all, there is this new feature. So what we're going to do is we're going to assign what we call an orientation. An orientation is just an indication of which direction along our curve is the direction that we're actually going to go. Right? We're going to revise the question from how much work does it take to walk this path pushing against this vector field. We're going to revise that to how much work does it take to walk this oriented path, this oriented curve, namely specifically in that direction, right? With the force being given. Okay, all right. So that's the new twist. And with that said, again, we've talked about how we're going to take, for any given little piece of curve, like that little piece of curve right there, we're just going to write down work as force dot displacement. No big deal. The force is, whatever it is, our vector field, roughly constant over that entire piece of curve because it's an itty-bitty, teeny-weeny little short little piece of curve. And then our displacement is going to be the linear estimate of displacement, namely our position differential dx. So on that little orange piece of curve, how much work does it take to move along that orange piece of curve? Well, force dot displacement, nothing to it. Okay, so then with the understanding that we want to add this up over the entire length of the entire curve, right, we're going to integrate, and as previously established, this dw is force dot displacement, f dot dx, and there you go, adding up over the entire curve. That's how we compute the total amount of work. Now, computation comes next. We'll get to the computation. Everybody with me so far? Okay. All right. So let's take a moment to recognize how this looks different from what we've seen before, right? So we have an integral over a curve. That's familiar. Yeah, but the integrand is a vector field. We haven't really seen that before. Not exactly, anyway. And then likewise, the differential, also a vector differential. That one's a little creepy, right? What does that even mean? Can you do an integral with a vector differential? Would be a pretty natural concern. But yeah, sure. I mean, again, the computation we'll get to in a minute. But just from a can you do this standpoint? Yeah, sure, because each little piece of curve has a corresponding displacement that we can linearly estimate. So really the main problem with this is we just don't yet know how to compute it. But conceptually, it's perfectly fine. Okay. All right, so thus the term vector line integral. And this is an importantly different construction from the scalar line integral that we saw last time, and thus the difference in terminology. Okay, now to the big looming question, how do we compute it? And I'm going to start by reminding y'all we've already established long ago this picture of what I'm going to call the major players in this story. All of these major players we've actually written down back in chapter 3. We talked about when you parameterize a piece of curve, there's ds represents our linear approximation, of course. The length of the piece of curve, and dx is the displacement, linear estimate, of course, along the piece of curve. And then don't forget the unit tangent vector, and of course the derivative is the velocity vector, all of which, of course, are parallel. And then further, don't forget that we have these relationships that we argued back at the start of chapter 3. I want to say 3.2. I can't remember for sure. Anyway, established long ago. And notice that allows me to rewrite my formula, or our expression that we had previously anyway, for a vector line integral, because our dx can be rewritten in any of those ways as established up here. And so we now have 3 different notations to choose from, you might say, for a vector line integral. So take your pick. By the way, a lot of books seem to have an odd, what I consider to be an odd preference for this third one. Say this. I'm a little uncomfortable with this third notation over here, because notice it looks a lot like a scalar line integral. It's got the ds on the end, like a scalar line integral. The integrand, being a dot product, is also a scalar, right? So it kind of conceals the fact that this is really representing something that's happening over an oriented curve. And scalar line integrals, as we discussed them and used them previously, there was no such thing as an orientation. So when things, this is just a philosophical point for me, but to me, when things are different, they should look different so you don't confuse them, right? And so I like, my own personal preference is this notation right here, because it does explicitly look different. From a computational standpoint, this is our big takeaway. From our computational standpoint, this vector line integral over a curve, I see, is a single variable calculus plug and chug integral dt. This is the pullback through the parameterization, plug and chug. All right, how we doing? Let me pause. Example coming up next, but who's got a question? Okay, so here we go. Let's do one. And what we have here is a wind is exerting a force on us as we walk. And here's a formula for the force that the wind is exerting on us. And we want to know how much work it takes us, you, whatever, to walk along our curve. And notice that our curve is explicitly given. Not only is the underlying curve given, top half of the unit circle, but notice it is an oriented curve, because it's specifically specified. Yeah, that was a bad construction there. It is explicitly specified that this is counterclockwise. Is that good, everybody? Okay. All right. So now we are pretty much just going to plug and chug. There is one little interpretation, little asterisk that we have to be careful about. This is a point of physics. This isn't a physics class, but unavoidably we're going to need a little physics here and there. And this is the idea of equal and opposite forces. If you haven't had a physics class, don't worry about it too much. The big idea is my stylus right there. There are actually 2 forces that are acting on my stylus. Gravity is pulling it down, as it does to everything. And yet it doesn't fall, because my hand is applying a force upward. and in exactly the opposite direction with exactly the opposite, or exactly the same magnitude, I guess you could say. So equal and opposite, right? And so there are two forces involved. And in a lot of these kinds of situations, there are actually two forces involved. So which of the two forces is the right one depends on how the question's phrased and what the question is asking. The question is asking, how much work do you exert? And if you want to know how much work you exert, you need to know how much force are you pushing with. And you are pushing against the wind. Right? Wind is blowing on you. You are pushing against the wind. So, so the point here is that if the force given is what the wind is doing, right, then you are pushing with the negative of that force. And thus this minus sign right there. Everybody good? So this boils down then to work as in, vector line integral of force dot displacement, and it's just we have to be careful to include the force that you are pushing with, because we want to know the work that you perform. Okay, so how to compute this thing. This is very plug and chug at this point. Notice as we discussed several pages. Oh, wait, where? Here it is. No? Yeah. As we discussed several, a ways back, the first thing to do is to parameterize. And so here we go. Let's see here. The unit circle is easy to parameterize. Specifically, we're looking at the top half of the unit circle, which, of course, we achieve in just these values of t, 0 to pi. We don't go all the way around, just the top half. Notice that this does have the correct orientation, right? Think about what you know about what this parameterization is doing. This is tracing out the unit circle specifically, as I'm doing with my hand here, right? It's going around this way. That's just how that parameterization is set up. And that is, as it's supposed to be, counterclockwise. So, we're all good. Everybody happy? Yeah.
If you said like clockwise, how would you?
Yeah, great question. I'm going to do exactly that in a few minutes. Yeah, so let me come back to that question. Yeah. Okay. All right. So per our formula up here, we're going to need to know x prime. Real easy to take that derivative. A little bit of calculus, nothing to it. We then plug into our formula. Right, vector line integral computed with this pullback, as it were. Note the minus sign carries along. And then again, it's very plug and chug. The x prime we just computed on the previous page. Boom. Right. Let's see here. The vector field we were given specifically, it was y comma negative x. Now, of course, we are pushing with the negative of that force, right? But the vector field that was given, the f that I have here, next to which I have already accounted for the oppositeness, right? The f specifically is y comma negative x. So don't double count the minus. It's easy to mess that up. And now the one part that students very often get confused about, and that is, what am I going to do with the x and the y that are right here? And let me just remind you again, the change of variables function, or in this case, the parameterization, explicitly tells you what x and y are. Using this pullback, x is cosine t, y is sine t. So we just plug that right in, just like it says. Y, I missed. Let me try that again. Y is sine t. X is cosine t. Single variable integral, plug and chug. How we doing? All right, I'm going to make a little bit of an eyebrow-raising assertion here, seeming a little bit of a surprise. But this expression right here, our vector line integral, I claim is even easier to compute than scalar line integrals. Now, this seems a little bit, how could that be? It's clearly a more sophisticated idea. We have this more sophisticated notion of an oriented domain that we've got to be careful about. The integrand's a vector. The differential is a vector. Everything's more complicated in some sense. But beautiful thing about it, you see right here in this formula that we're just plugging into, I don't need to compute the magnitude of x prime. Right? When you're doing a scalar line integral, the stretching factor was the magnitude of x prime. Magnitudes involve square roots. Square roots tend to make for bad integrals. Right? So this one, now the magnitude is still in there. It's literally one of the factors inside of x prime itself. I just don't need to compute it. All I have to do with this x prime is just dot it with something. No square roots. So a little counterintuitive, but the more sophisticated construction tends to be easier to compute. So that's nice. Got to love it when that happens. Okay, now, when we were doing scalar line integrals, we were very happy to find out that you can use any parameterization that you like. Doesn't matter. Go crazy. Whatever. No such luck. Here, the parameterization does matter. But it only matters in one way. The only way that the parameterization matters is that it has to go the same direction that it's supposed to. Keeping in mind, we're not parameterizing a curve. We're parameterizing an oriented curve. So your parameterization has to go the same way. It has to go the indicated direction for our oriented curve. And other than that, doesn't matter. As long as your parameterization has the right orientation, use any parameterization you want, all good. You get the same answer no matter what. Okay. Now let's think about what would happen if you have the wrong orientation. And I'm going to come back to this. Let's see where. Yeah, here we go. I'm going to come back to this picture right here. If I were going the wrong direction, let's look at this term. What happens to this term if I'm going the wrong way? Well, if I'm going the wrong way, then instead of my dx vector being that, going the wrong way, my dx vector would just be that. My dx vector would be the exact negative of what it should have been, which means that my dw will be the exact negative of what it should have been. Therefore, there will be an extra factor of -1 in every single term in this summation, which means the answer I get will be the exact negative of what I should have gotten. So that's a nice little punchline here. If you parameterize backwards, you'll just be off by a factor of -1. Pretty believable, I hope. And I'm going to formalize this using the book's notation. You can see they use a superscript of a minus to indicate going the opposite direction. So given a curve C oriented one way, C minus, exact same path, just going the other direction. It's very nice to have a handy little notation for this idea. And the theorem that we already just kind of talked through the intuition of basically just says if you go the opposite direction, then you're going to get the negative of the right answer. Or the negative of the answer that you would have gotten if you'd gone the other direction. What do you think? Is that believable? Okay, so that brings me to my next example, and I'm going to show you three, four, it depends on how you count, certainly three perfectly acceptable solutions for how, this is to your question, what if we're going clockwise? And if you're going clockwise instead of counterclockwise, you can still just parameterize this curve. And what I want to focus on now is how do we parameterize a clockwise oriented unit circle. There's a couple different ways that you can do this. A couple of different ways to think about how you would do it anyway. So here's my first idea. Notice if you are indeed going clockwise, then over here is where you start. This is where you might want to call t equals 0, given the direction that you're actually going. Right? And then, it'd be tempting anyway to call this t equals pi over here. Because that's where you end, and that total angle anyway is pi. So with this in mind, there's a pretty reasonable case to be made that what we're doing is we're thinking of this as being our angle t. Now, that does not play nice with trigonometry. Trigonometry is set up to be that other angle. We'll talk about that in a moment. But what I'm looking for, case can be made, is I am looking for position x comma y as a function of that angle t, because then when t equals 0, I'm here. As t increases, I move in the direction I'm supposed to, and at t equals pi, I'm done. Okay, so now the question remains, how do I describe the location here in terms of t? So here's my next trick here, and that is if this angle is t, then this angle, of course, is pi minus t, and now I can kind of momentarily forget about t and look at this, what I have here. I want to know position on the unit circle, and I know this angle. This really is the good old regular trig theta, right? Measured from the positive part of the x-axis, all the usual thing. And so I can immediately write down cosine theta sine theta. And I just have to remember that theta is, of course, not t, it's pi minus t. What do you think? Everybody good so far? And then you'll recall, of course, I made this observation, whatever we're going to call it, statement, some time ago, that you do need to know angle addition formulas. High schools very often let that slide. That's unfortunate for people who are going to come and do engineering or higher level math classes at Duke. We do need you to know the angle addition formulas. So make sure you know these, and if you just plug in the angle addition formulas real quick here, this simplifies to that. And so we have ourselves a parameterization, and as desired, it goes clockwise. We happy? Okay, now here's a different way you can do this. This is just a point of view, different way of thinking about it. Again, we want the clockwise parameterization. I want to know how to do that. How am I going to figure out that blue parameterization? Recalling, though, that I already know how to do this. I already know how to parameterize this green-oriented curve. Starting here, going counterclockwise. This is our very first parameterization we ever wrote down. So I know the green parameterization. I want the blue parameterization. And the easy observation to make is that they are reflections of each other. More to the point, the blue is the reflection of the green. And so I can literally write down then that the parameterization I'm looking for is the reflection over that line of the green parameterization I already know. And now I just have to figure out how do I actually execute that reflection. And I think it's a pretty easy pitch that when you reflect over the y-axis, the y-coordinate stays the same. The x-coordinate just gets a minus sign, right? And so that reflection just gives us that minus sign right there. Everybody good? All right, and so good news. Notice that the parameterizations that we got using these two different methods, right, are in fact exactly the same. Not that they have to be, but it's kind of cool that they are. This is just two different ways to argue the same parameterization. And then, plug and chug and off you go. What do you think? Everybody good? By the way, I've made this observation before. This is the tools for your toolbox metaphor. Yes, we got the same parameterization two different ways. Remember, your focus in times like this is not on what is the answer, right? But the focus on should be what were the ideas that allowed me to reason to the answer in this case, right? So tools for your toolbox. So this idea of visualizing, geometrically indicating and visualizing what your parameter is on your diagram, and then using geometry, trig, etc. from that to conclude your parameterization, that's a neat trick, right? It's a nice tool and something to keep in mind. This idea over here that, if you're trying to do one parameterization, try to geometrically relate it to something you already know. Also a pretty cool trick. Applies in far more than just this one circumstance. So try to, think about how you can, generalize these little strategies that we've used here for future benefit. Okay. All right, now here's the third solution I'm going to show you. Third solution doesn't involve parameterizing at all. The third solution is to make the observation that, hey, this curve we just got asked about is the same as the original curve we were looking at, just oriented the opposite direction. And then observing that, what is the effect of going the opposite direction? The effect of going the opposite direction is just to add a minus sign. And then lastly, we know we're going to get the negative of the answer we got to the original application, and of course the original answer was pi. And so, boom, right, 3 easy steps. No new parameterization required here. And same answer, of course, better be. Right? And we're good. So really, this is kind of the best answer in this context, because we'd already computed this green integral. Right? We already went to a bunch of trouble to crank out this green integral. Here, we're just piggybacking on having already done that work. Is everybody happy with that? Okay, now let me show you a fourth. I'm going to say argument, but then I'm going to complain pretty severely about this fourth argument. I'm not encouraging this. In fact, the only reason I'm bringing this up is to try to discourage you from making the following argument. And it goes something like this, going back to the original computation that we did here. All right, we parameterized, blah, blah, blah. And some students will make the case that, okay, here we were going from 0 to pi. That's what ended up making this counterclockwise. If I want to go clockwise, I could just go from pi to 0. Right? Shouldn't I, it would seem, right? Shouldn't I be able to take this integral and just make the bounds be from pi to 0. Let's let t, time, start at pi and end at 0. So the argument kind of goes, right? Now, let's step back for just a quick minute. Now, what do we think about this idea that we could try to make a case, we could try to make an argument based on the idea that time is going to move backwards, right? And I got to admit, I'm a little bit weirded out by that, right? What do you mean time moves backwards? Are we in a science fiction movie, right? I think it's a good idea in general to try to keep your arguments clear of all references to time travel. It's a spooky idea, right? So now, counter argument to the counter argument. This will give us the right answer. It does give us the minus sign, just like an argument that I made myself. And again, it's not about the answer, it's about the reasoning, it's about the argument. And arguments about time travel, I think, are fundamentally weak and unsatisfying. Whereas we made here an explicit case for when you go the opposite direction, these two dx's are literally the negatives of each other. There's nothing mysterious or sci-fi about that. They're just straight up exactly negatives of each other, and so much more reasonable argument here. So please don't do this sort of thing. Please no time travel arguments. I think that's quite weak. Again, it doesn't buy you anything, right? It's just a contorted and confused way to introduce a minus sign. That's much easier to introduce just citing this theorem. No sci-fi required. Okay. All right. Is everybody on board with that? Yeah. Okay. All right. So next thing we're going to talk about is other applications of this idea of a vector line integral. So reminder, we have just gotten through talking about, whoopsie, wrong tool here. We have just gotten through arguing that a vector line integral represents work. That was our motivating example. And the reason we got work is because the vector field itself was representing forces. And so when you can look right at this expression, f dot dx literally is force dot displacement, thus work. Right? Everything kind of fits together. Okay. Here's the thing. We can use vector fields to represent other stuff. For example, a vector field can be used to represent a fluid flow. Specifically, we just interpret the field vectors as representing the velocities, for example, the velocities of the fluid in different places. Well, if that's the case, no forces anymore. Right? If our vector field represents velocity of a fluid, now what does this represent? It's not work anymore. This is no longer force dot displacement. Now this is velocity dot displacement. And velocity dot displacement. Okay, so what does that even mean? Right, physically. How am I supposed to, clearly if my vector field represents a fluid flow, then there's a physical scenario we're addressing. So this has got to represent something physical. It's definitely not work. So what is it? Okay. So I'm going to answer this question in a little bit of a weird way. By the way, all of this down here is just a recopy in case you might find it convenient. This is just our, again, the major players and their relationships and our different ways to write down a vector line integral. Nothing new here. What I'm going to do to answer this question of, what if I'm talking about a fluid flow is I'm going to kind of argue it backwards. Instead of taking the vector line integral and trying to make an interpretation of it, I'm going to start with a physics question, an unexpected, weird, seemingly unnatural physics question, and it's going to turn out that the answer is going to be a vector line integral, as it turns out, right? So this is going to come at you kind of backwards. It's the nature of the beast. Sorry about that. But bear with me, and it's all going to work out. So here's the question. Let's see here. We have a curve like so. That's our curve C. Now, I want to consider what I'm going to call this thin region around C. So not the curve itself, right? But I'm going to look at this kind of it's like a fattened up curve. It has a cross-sectional area. I'm going to make this a constant cross-sectional area A. We'll come back and see how that plays in a minute. But I want to consider this thin region that follows this curve with cross-sectional area A. Why I would want to do such a thing has yet to reveal itself, right? So for the moment, just let's proceed. Here's the question I want to ask, keeping in mind that our vector field represents the flow of a fluid. So there's fluid running around here. This yellow region, there's fluid in that yellow region. And altogether, if I'm interested just in that fluid there, here's my question I want to ask, looking just at that fluid in R. Grand total, looking at all of that fluid, to what extent is all of that fluid flowing along the curve? Again, completely unmotivated question, right? This is coming out of thin air. And nevertheless, we can still answer questions that are coming out of thin air. Okay. All right. Well, here's how we're going to do it. I'm going to break this region here. I'm going to break it up into chunks. For example, here's a chunk of fluid, right? A chunk of fluid associated to just one little piece of my curve. And that little piece of fluid, I can talk about how much fluid there is there. The volume, in other words, of that little slice of my region. And of course, it's going to be the cross-sectional area times the length ds. So that's just a little bit of geometry there. Yeah? Okay. Let's see here. Now, the vector field representing the velocity, that piece of fluid is flowing about like so. And so you got to kind of imagine this little piece of fluid is going to be going that way, right? But keep in mind, that's not what I'm interested in, right? The question says, to what extent is it flowing along the curve? So I'm not interested in the actual velocity. I'm interested in this component, the component along the curve. And that component is, of course, computed with dot product with the unit vector, unit tangent vector. So, in some sense, this is the answer to the question for that one little piece, right? This represents, for this one little piece here, this represents how much that fluid is flowing along the curve. And I can then say, okay, well, I'm going to add that up over the entire curve. And you just plug in the formulas, kind of move things around, and here we get our final punchline. Good idea to follow through these details. Let's see here. Yeah, but our final punchline for the question that we asked is that expression there on the right. Okay. How are we doing so far? The interpretation's the next thing I'm going to talk about. Okay. So I want to start by talking about this cross-sectional area right there. Keep in mind that that was one of the initial parameters, and I'm going to say that cross-sectional area being a factor in this answer is well, yeah, of course. I mean, you think about it. I mean, the bigger the cross-sectional area, the more fluid there is. And the more fluid there is, then the more fluid flowing along the curve there is, because there's more fluid. The fact that there's a factor of A in here is well, of course. So, in fact, I would take the point of view that this is sufficiently clear that I don't really want that to be even part of the question. I kind of want to revisit the question. I needed to talk about some actual cross-sectional area so I could have an actual volume so I can actually write stuff down. But really the better question to ask is, per unit area, obviously more area means more stuff, but per unit area, how much is the fluid flowing along the curve. And per unit area is an easy thing to address here. I'm just going to take this area and divide it over here into the denominator. And having done that, the answer to the question then is, how much fluid is flowing along the curve per unit area? Oh, well, then the answer is the vector line integral. And as promised now, we now have an answer to the question of what does that vector line integral represent? That vector line integral represents the rate that the fluid is flowing along the curve per unit area of cross-section, of course. So the takeaway though, the way you should think about what a vector line integral represents in the context of a fluid flow is, in some sense, how much the fluid is flowing along the curve. Okay, so that's the argument. How are we doing? Let me pause on that for a quick second. Does everybody buy it? All right. Okay. By the way, very important bit of intuition to have when you take a fluid dynamics course at some point. How much the fluid is flowing along in different directions, and specifically how much it flows along a curve, turns out to be extremely interesting, extremely useful. When you write down the equations that ultimately describe how an airplane wing works, right? Kind of a big deal, right? Well, it involves looking at literally how much and to what extent we have how much fluid flowing along the sort of the perimeter of the cross-section of the airplane wing. And so this construction and this interpretation, tremendously important in those applications, right? So this is not sort of, abstract, silly mathematician games, right? This is extremely natural in extremely important applications. Okay. All right, now here is a variation. This is a very slight variation. We have our existing interpretation of vector line integral, the extent to which the fluid's flowing along the curve, per unit area, blah, blah, blah. And the one little twist we're going to make here is we're going to consider the special case where the curve is closed. Same idea of a vector line integral. Fluid, vector field, velocity, extent to which the fluid's flowing along. That's all the same. We're just going to consider what do we make of this if the curve is a closed curve? Namely, it sort of loops back around on itself, starts and ends at the same point, however you want to say that. And in this case, altogether, we call this circulation. So circulation just means vector line integral, where the integrand represents the velocity of a fluid, with the asterisk being that it has to be a closed curve. Now let me give you a quick example of a situation where you might have heard the term circulation. This goes back to when I was a kid, and at our house, certain doors had to remain closed and certain doors had to remain open, and it had to do with the air conditioning. And well, we want to make sure that we get circulation from the air conditioning system, right? So what does that mean? Circulation of the air conditioning system. Well, up in the attic, there's a contraption up there that gets cold, right? And air is blown over the cold thing. That makes cold air, which then gets pumped into the house. Okay, but there's only so much volume in the house. If you're pumping cold air in, you're going to have to intake some of the other air back up into the attic to make room for the cold air, right? So cold air into the house, warm air out of the house. The warm air goes and gets cold. The cold air goes and cools me off and becomes warm again, and around it goes, right? So circulation is what makes that possible. And if you think about it, that's what we're talking about here. We're talking about a fluid flowing along a closed curve. Right? So, anyway, natural terminology in that sense. Okay, let's see here. It sounds like we're getting close to being out of time. Oh, we are literally out of time. Okay, we'll draw the line right here and pick it up on Wednesday. Y'all have a good one. See you later. Don't forget about attendance.